Hello, everyone. Welcome to lecture 20 on the finite element method, ME 362. Again, we start with our, let's say, with our roadmap. And as you remember, I mentioned that this roadmap holds whether you talk about one-dimensional FEM or two-dimensional FEM. We also talked about different sources of approximation in a finite element scheme. And in particular, we mentioned that within finite element, you do not approximate only the solution, but you approximate the equation itself and as well as the input to the problem. This was a more elaborate roadmap, which we established together when we talked about the one-dimensional finite element method. And then we had this short overview of 1D FEM. And I repeat that because I need you to remember this, because the steps that we are going through in two-dimensional FEM are similar to this. Again, the steps are similar in a sense that you start with a strong form, you multiply by a test function, you integrate over a test function, and after some mathematical steps, you come to some sort of KU equals F system, and then each component of that stiffness matrix is now related to some derivatives of shape functions and something that we call Jacobian, and then you integrate it and you do that integration with Gauss Quadrature rules, and then you write that as a summation over the Gauss points. This thing also exists in a two-dimensional FEM. So if you have a two-dimensional FEM, again, you would have some sort of a stiffness matrix and its components would be related to the derivatives of shape functions, but now the shape functions will be in 2D. And then in order to integrate that, you transfer that into the natural space instead of the physical space, and you also do the summation over the Gauss points instead of integration. All right, with that, we want to come to two-dimensional FEM. Because I just now mentioned this connection of the, let's say, a stiffness matrix, let me just draw it for you. So in a 1D FEM, you have this element, and then you have, let's say, node 1, node 2, and you can imagine the stiffness matrix would be 2 by 2, and it looked like K minus K minus K, K. All right. So this is one element, and you remember if you had, for instance, 2 elements or 3 elements, it doesn't matter, you can assemble them together into this big assembly or big assembled matrix of the system. Now, if it's a two-dimensional finite element, for instance, think of a triangular element. Now, the area inside is filled. It is not just 3 truss elements. So if you think about these are 3 truss elements, okay? So these are 3 one-dimensional elements that you have in a truss structure. But the picture on the right, it has area inside, so it's a two-dimensional finite element method. And now, if you think about this, it also has a stiffness matrix, which is now 6 by 6, okay? Because each of these points, they have 2 degrees of freedom, or these nodes, and then you have 3 nodes, 2 degrees of freedom each, you have 6 by 6. Interestingly enough, you can imagine if you talk about the same problem also here, even though you have 3 truss members in a two-dimensional structure, you would end up exactly also with a matrix that is 6 by 6. These are not equal, only the dimensions are equal. But again, this would be like 3 truss members. And this one is actually a 2D element. But in the left picture, also you have 3 nodes, and each node has 2 degrees of freedom. So eventually your stiffness matrix would be 6 by 6. All right. So you know how to calculate the, let's say, the left stiffness matrix. Now we want to go to the right one. All right. So this is again the map of the finite elements method. And in order to proceed with two-dimensional FEM, we had some mathematical preliminaries. In particular, we had this Einstein summation convention. And we also learned about dot product and the so-called double dot product and this dyadic product. So it's a different type of product. And then we had the notation that we refer to as Kronecker delta. And based on these definitions, we also write our stress-strain relationship in a more elegant form, because now you have basically this double dot product in between. And this notation also allows you to extend the concept of derivatives more elegantly. And the reason for that is that this prime, that usually in a one-dimensional problem, if you are dealing with scalar fields, prime means their derivative. Now, if you have a vectorial problem or tensorial problem, these derivatives, they have different versions or different natures. And for instance, if you think of a vector u, you can think of three types of derivatives for that. It could be a gradient, it could be a divergence, it could be a curl. We don't talk about curl in this course, but then gradient and divergence of a vector, they are important. And also, if you think of a matrix or a second order tensor, you can think of a similar story. So you would also have gradient and divergence of that. We showed that the gradient of a scalar field, it reads like this. So this is the gradient for a scalar field. And then if instead of that you had a vector, this would be your gradient. So now gradient of a vector is a matrix or is a second order tensor. If you have a vector valued function, now the divergence of that is a scalar as opposed to its gradient, which was a matrix. And then eventually, if you have a divergence of a matrix or a second order tensor, it becomes a vector. And the summary of all of these would be this. And these are the things that we are going to use in what follows. So a gradient of a scalar field, it would be something like gradient of temperature. So when you are dealing with a thermal problem, this is what you need. Divergence of a second order tensor, this is something like divergence of stress. So you would need something like that when you are dealing with a mechanical problem. Divergence of U, this would look like divergence of Q, heat flux, again, for a thermal problem. So this, let's say the left-hand side is useful for a thermal problem. And the right-hand side would be useful for the mechanical problem. And obviously this one, the gradient of U is nothing but strain itself, right? Or the symmetric gradient of U is strain, but that's how it works. So basically, on the left-hand side, you have temperature gradient, let's call it G, and then you have maybe heat flux, and then there is a connection between them, which is the Fourier law. And then on the right-hand side, this would be strain, and then let's say divergence relation would relate to stress, and in between you have the Hooke's law. Okay, so this is how everything fits together. And also in view of that, you can think of this big picture of mechanics. Again, in a mechanical problem, you want to connect deformation to load. In a thermal problem, you want to connect temperature to heat flux. But then eventually these operators, gradient U, and then this, let's say, well, gradient of U and gradient theta, you see it here. You don't see divergence of Q and divergence of sigma because they are in the next slide. So, but those will be also relating to your governing equation or your balance equation. And these are how the strong form or the balance equation look like for a mechanical problem and for a thermal problem. For most of the derivations, I stick to the mechanical problem because it is more complex. As you can see, you are dealing with a higher dimension compared to a thermal problem. But eventually in that homework 6, we will show how you will do also a thermal problem. Okay, and then if you want to focus on 2D, and that is what we want to do for now, you would have a shorter, more compact version of those equations, but everything that holds for 2D in principle also holds for 3D. All right, so now, if you remember what we did in our roadmap here, we went from strong form to weak form, and then we talked about these approximations, and we learned these shape functions here basically. Okay, so we did this step first, and then we did this step afterwards. Now we want to switch this order. We start with approximation now, and then we talk about this connection in the next lecture. So today we want to talk about approximations using two-dimensional finite element method, or two-dimensional finite elements. The methodology itself is not there yet. So let's call it approximation using two-dimensional finite elements. Okay. And then again, this is just a fancy name or fancy title to tell you that we want to learn about shape functions in 2D. All right, so this is what we want to do. We want to learn about shape functions. And similar to what we did in 1D, I'm going to teach these via an example. So if you remember in a one-dimensional analysis, I gave you this simple example. I asked you, for instance, if you know f at, I don't know, f at 0 is 5, and f at 1 is, I don't know, 15. If I ask you what would be f at 0.5, so this is the question. If I ask you what would be f at 0.5, you would immediately say that is 10. Okay, which again, we learned that this thing that you basically did in your head is that you connected a line between these two. So you thought, well, at 0 you have 5, I don't know, at 1 you have 15. You connected this line, and basically you approximated that value using this linear approximation. Okay, so this is what you did. This was a 1D example. And then we learned that instead of doing this, what you could have done would be to say, well, f as a function of x is simply n1 times f at 1, or f at node 1, plus n2 and f at 2. And then in that case, this would be node 1 at 0, and node 2 would be at coordinate 1. Okay, and then using the shape functions, basically you can write the equation for this line. So if you do that intermediate step, so you know how to calculate the shape functions, you know what are the values of your functions at the 2 points at node 1 and node 2. And if you do that, you would end up with your line equation, which is, I don't know, is it, I think it's 10x plus 5, for instance. Okay, so let's say this was your intuitive approach. And the second one, the yellow one on the right-hand side, this was our approach using shape functions. So this is, maybe we call it FE approach, finite element approach. And then again, for this specific example, because it's so simple and it's linear, there are 2 points, you can imagine that doing something like this is an overkill. But if you have more points and if you have more dimensions, and especially if you need to program that and you need your computer to do that, then to have something systematic like the one we have on the yellow side is more important. So what we want to do now is to extend this to a two-dimensional problem. And you can immediately see why and how these shape functions would be useful for us. So now in a two-dimensional problem, the domain at which you have these values, it's going to be a, let's say, a square, okay, in its simple form. So let me just draw a, let me try to draw something like this. No. Sorry. Okay, finally. So let's say this is your domain. We have 4 corners. And now for each of these corners, we have a certain value given to that function. So this would be corner 1, this would be corner 2, and maybe we just go counterclockwise. So I'm going to call this thing, let's say, corner 3, and then this one would be corner 4. All right, so these are your corners. And also, just to give you a feeling about this, there is a coordinate system attached to this, obviously. Okay, so you can think of this thing as being your coordinate system, and then there is this third direction. Okay, so let's say this is your third direction. This is where you have your function f, and this coordinate system, it could be x, y, z. So you can think of it as x, y, z, but don't do that. For now, let's just think of it as xi eta instead of x and y, and then f is the value. So this is xi and this is eta. And then again, it is written like this is eta, and this is the same xi that we had before. Okay, so now for each of these, you have a value given at those points, okay? Or at 4 different points, you can also have values. So let's think of it this way. For instance, I know the value of the function at these 4 points. Let's call these points, I don't know, A, B, C, and D. So if I tell you that the value of that function f at point A, and point A is, by the way, the coordinate of point A is, for instance, -1 and 0, is, let's say, 2.5. Also, let me make it clear to you that I assume that so this is our coordinate system in terms of the directions, okay? But I am assuming that the origin of this is actually here. So if you want to think about it, this is your coordinate system, really. Okay, so the coordinate system is at the center. Those are rather the, let me just draw these lines to make it more clear for you. Okay, so this would be your coordinate system. This is xi, and this is eta, in a sense that the point at the center, this is your origin. This is 0, 0. Okay, I am doing this on purpose because I want to identify, or I wanted to emphasize that the center of your coordinate system may not be one of the nodes of the elements. It may not be one of the corners, but also it may be. So these are details here. Okay, so now let's say if we assume this is the center, and for now, let's assume the domain here has the size 2. Okay, so node 1 would have the coordinates -1, -1. Node 2 would have coordinates -1 and 1. sorry, 1 and minus 1. So it's 1 in c direction and minus 1 in eta direction. Coordinate 3, it is 1 and 1, and coordinate 4 is minus 1 and 1. Does that make sense? So these are the 4 coordinates. And what we have now is the value of that function at 4 points, which are A, B, C, and D. And by the way, pay attention that everything that we do here is an example, right? So there is nothing generic about this, but it's an example to just teach you how we need approximation, or how the approximation works and why we need these approximations. So at point A, which is at the coordinates minus 1 and 0, so in the eta direction or in the y direction, if you think of it, it is 0. In the c direction is minus 1, and let's say the value is 2.5. Point B, now the coordinates of point B would be 0 and minus 1. So c is 0, eta is minus 1. And let's say at that point, it's 1.5. And then point C, which is at 1, 0, let's say it's 0.5. And maybe point D, that is at 0, 1, that's going to be 1.5. Okay, so now you have the values at 4 points of a 2-dimensional domain. Again, remember, if it was a 1-dimensional problem, you would need the values at 2 points of a line to make a line. Now you have the values at 4 corners of a surface, okay, or of a square surface. So what you want to do is to calculate 2 things. The first question I want to ask you, or I want you to answer, is that if these are the values, for instance, that you have, what would be the value of f at the center? Okay, let's say at 0, 0. Could you answer that, for instance? Okay, what would be that? The other thing is that we say we are not looking only for a specific point. I am just interested in the function itself. So that function, it would be a function of c and eta. I want to know what is that function in the first place. Does that make sense? So this is, let's say this is example 1. Just sort of remember this example for now. But also I want to show you a variation of this example that may be more friendly for you. So this is exactly looking like the same thing, but now I'm going to change these corners. So instead of assuming A, B, C, D to be here, you can assume them to be on points 1, 2, 3, 4. Okay, so you may as well just say, so let's think about this one. This is example 2. But you can also think of a variation of that, possibly a simpler version of it. That's example 1, but it's the same question. I'm going to just change this and change these coordinates to the 4 points. So these 4 points now could be at point 1, at point 2, at point 3, at point 4. So point 1 is minus 1, minus 1. Maybe point 2 is 1, minus 1. And then point 3 is 1, 1. And then point 4 is minus 1 and 1. You see, now it's a similar example, but it's not the same example. So I'm just giving you now the values at 4 corners, but the question is the same question. What is the value of that in any specific point or any generic point? So if it's a generic point, it's just in terms of xi and eta, and if it's a specific point, for instance, you have the coordinates for that. So this is the type of problem or the type of examples you need to think about. Okay, so what you need to do is obviously very similar to what we did before, but as you can see, it is not just like a 1D problem. It's not that simple problem that you can just connect two nodes. You have 4 nodes. You need to actually construct that function and evaluate it, and that's exactly what we want to do. So what you need to do is to use shape functions now for this, and that's exactly what we are going to do together. Please feel free to interrupt me if you have any questions. Okay, so what I want to do is to use shape functions to answer this question. And again, I think you can see it here. You could define that function f as sum of NIFI. So if you multiply N1 times the, again, N1 in this case, it would have specific coordinates. And this Fi would be the values of f at those coordinates. Those coordinates may or may not be on the, on the corners. So this is a more complex problem if you want. The previous one, example 1, is nicer because you immediately see that at each node you have those values, okay? So here, your f, let me start with this, would be N1 times F1 plus N2 times F2 plus N3 times F3 plus N4 times F4. Okay, so if you do that, now you remember this N1, it has this nice property that it is 0 everywhere, but it is 1 at point 1. So how would that look? It would look like a surface like this. It's going to look like that, basically, if you think about it. It's going to be a surface which is 1 here, and then it's 0 on these other corners. So if you take that function and you multiply that by the value of f at point 1, then you are certain that at point 1 you get f1, and everywhere else you get 0. So basically that's it. That's an exact approximation for point 1. So you do this addition, so you get an exact approximation for the 4 corner nodes, and obviously that tells you that your shape function, or your function, this approximation function, is exact at the nodes, and then everywhere else it's an approximation. Now, you can extend the same story here, but you need to be more careful, okay? Because now this N1, it is something that is 1 here, okay? Whereas this point 1, you should remember it's not coinciding with the function itself. So in this case, when you use these shape functions, you need to use them in terms of xi and eta, and then for those xi and etas, you can use coordinates of a, b, c, and d. All right, so you can also evaluate them and extend that idea. So my point is, what we had here is perfectly similar to what we did in 1D. We didn't do exactly this type of the example in 1D, but you can also do that. All right, either way, the problem boils down to shape functions. What are these n's? What is n1? What is n2? What's n3? And what is n4? All right, so we want to define N1, N2, N3, and N4. Okay, what is Ni? Let's just write Ni and its property. Ni, for any I, what was the property it had? It is 1 at node I, right? And 0 elsewhere. And 0 at other nodes. Okay, so if we want to construct that for this example, as I mentioned, you are thinking of something which would be, for instance, 1 here at node 1, and it's 0 here and here and here. So it's going to look like a surface which is going to look like this. And then, I don't know, maybe I draw this line to make it clear that it's a surface, right? It's going to be a surface like this. Okay, so you are talking about that surface. What is the equation of that surface? All right, so how do we do this? We play exactly the same game that we played before. You are looking for something that is 0 here and is 0 here and is 0 here, but it's 1 here. So remember how we did it in 1D? If you had this problem in 1D, you would, for instance, if you want to construct N1 in 1D, you do what? You would say N1 is something that is 1 at node 1. So N1 in this example would look like that. So, I mean, it's 1. So it's 1 at node 1, which in this case is 0, and it's 0 at node 2, that in this case is coordinate 1. So what you did, or what we did together, was to write it something like this: x minus 1. This makes sure that at coordinate 1, which is node 2, this is 0. Okay, so you make sure that at other nodes it is 0, and then you make sure that it is 1 at node 1. So then you insert the coordinate of node 1, which is 0, and then you get -1. So that's not good. Then you divide this by -1, and that's it. So that's how you construct N1 in 1D. You play exactly the same game here. You are looking for something that is 0 here, here, and here. So that means it is 0 on this line, and it's 0 on this line. So what are the functions of these lines? This line is eta equals 1. This line is xi equals 1. Right? So what you need to do is to make sure that on those two lines, this thing is 0. Or otherwise, whatever it is, it's going to look like, I don't know, 1 minus xi, or let me write it as, how did we write it in 1? Yeah, 1 minus, yeah, if I want to write it similar to this, I write it as xi minus 1, so it's something that looks like xi minus 1 times eta minus 1. Okay, now you are having a function which it is definitely 0 here, it's 0 here, and it's 0 here. That's exactly what you wanted, right? But the problem is that if I insert the coordinate of node 1, would it give me 1 or not? So the coordinates of node 1 are -1 and -1. So if you insert -1 for xi and -1 for eta, you get -2 times -2. Okay, so you get a 4 basically. Now, in order to make sure that you get 1 for n1 at node 1, you multiply that by 1 over 4, or you divide it by 4, basically. All right? So that's how you construct, or you write n1. Now, this was n1. Then we have n2. You play the same game. For n2, it would be 1 over 4, say c plus 1. Okay, if I write it as eta minus 1, there must be a minus here. I hope I don't make mistakes, but you get the idea, even if I make mistakes while writing them. So that's plus 1, and then there is minus 1 over 4, c minus 1, eta plus 1. Does that make sense? Is that good? Okay, so now I want to go to that first example, and I don't go through the second example. I leave the second example as an exercise for you. It's not something that we want to do. It's not something that necessarily is helpful, but I think for you, it's important that you realize what's happening. I want to go to that first example and just solve this together. In the first example, also, I think just to be consistent with my notes, if you don't mind, I'm going to change these values slightly. Okay, so let's say these values are not exactly what we have written. These are, you will see why I'm doing this in a second. So this is 1, 2, minus 1, and 4. Okay, so let's say you have the values at these 4 corners, and based on the shape functions that we just learned together, we want to calculate this approximation. So we know these are the shape functions, and we know how to write f. Does that make sense? So what I want to do now is to use those shape functions with these values. Again, if I want to write the values here, so we want something that is 1 at node 1, it's 2 at node 2, it's minus 1 at node 3, and it's, let's say, 4 at node 4. So this is the first example. Now, as we just learned together, f in terms of xi and eta would be n1. Remember, n1, n2, n3, and n4, these are all functions of xi and eta, right? So using them, it allows you to express your functions in terms of xi and eta. So this is a function of xi and eta only. This is a function of xi and eta. The same here, the same. So basically, you have something which looks like n1 as a function of xi and eta f1 plus n2 as a function of xi and eta f2 plus n3 as a function of xi and eta f3, and n4 as a function of xi and eta f4. Now, these are functions of xi and eta. These are just numbers or coefficients. So what you get is a function of xi and eta. And as we spoke together, this is now a summation basically over ni being a function of xi and eta times fi. And I goes from 1 to 4. And instead of 4, I write NPE, node per element. So this has that. And then again, because we learned this Einstein summation convention, I'm going to just write it like this, because if you have an index repeated twice, it means a summation. All right, so you have that. And what I want to do now is to basically replace those shape functions. So you know this is what you will have, right? This is the summation where you need to use to construct that f together. All right. So to do that, we use the ends from here. So I will just copy I will just copy this into that other slide. Down here maybe, or up here. Okay, so now you have the ends. Let's write down our f. It's going to be f f1 times n1. So again, n1, see, n1 is 1 over 4 c minus 1 times eta minus 1 times f at 1. So that's the value of the function at point 1. So that is 1 minus 1 over 4 c plus 1 eta minus 1 times the value of the function at point 2. That's a 2. And then you have plus 1 over 4 c plus 1 times eta plus 1 times minus 1, and eventually minus 1 over 4, 1, well, c minus 1 eta plus 1 times 4. Okay, so if you do that, you get a function of c and eta. So that's your function. So this is your function f as a function of c and eta. You may or may not expand it or simplify it, but this is basically what it is. Okay, so even if you don't expand it, this is good enough. But why am I doing this? Because I want to show you this other thing. The first question was that what would be the value of the function at 0, 0? So now that you have this, again, whether you have expanded or simplified it or not, you can already insert 0, 0 into this and calculate the value of the function at 0, right? So I'm going to just take this as the form that we deal with. And using this, we try to answer that first question, 0, 0. At 0, 0, so if this is 0, this is 0, you would get 1, you would get 1 over 4 from the first one, right? So you get minus 1 times minus 1, that's 1 times 1. So you get 1 over 4. Good. Then from the second one, you get minus 1 here altogether times minus 1 over 4. So 1 over 4 times 2, that is 2 over 4. Then from the third one, you get minus 1 over 4. So again, 1, 1, minus 1 over 4. And from the last one, you get a minus 1 here, a 1 here, 1 over 4 times 4, that's a 1. So if you look at this, this gives you 1.5. All right? So that's the answer, first of all. That's the value of the approximated f at point, at the center. Let's call it maybe point E, if you like. So you can then say f at E is 1.5. So this was the key question. Fe is, I don't know, 1.5. But also, if you play this game, and this is why we had that other example that I said I wouldn't do. So remember, we had this also example 2. So if you play this game and you calculate f for points A, B, C, and D, in fact, you will get the values that I gave you in that other example. So these two functions, they are the same surface. They are just two different examples. So in this example also, if you do exactly what we did before, so here you just use this fc eta that we have from the previous one, and then you calculate that at A, at B, at C, and at D. Also at A, you get 2.5, which means C is, again, -1, eta is 0. Then FA would end up being 2.5. If you do it at B, that is C0, eta is -1, FB would be 1.5. Now C is 1 eta 0 at point C, so that gives you F at C is 0.5, and then eventually C is 0, eta is 1, and that gives you F at D is 1.5. So my point being that now if you compare these four values, 2.5, 1.5, 0.5, and 1.5, these four values are the same values that I gave you in example 2. So the example 2, I leave it as an exercise for you. But my point is, if you do example 2 and if you do it correctly, you should end up with the same function. Okay, so the surface is the same surface. You just construct it via 4 different points. Okay, so you can imagine there are infinitely many combinations of 4 points that give you the same surface. Okay, so these are 2 nice examples, and I think they are sort of complementing each other. But also it is now why we have it. If you look at this, at point A, I have 2.5. At point at point A, I have 2.5. At point C, I have 0.5. Okay, so if this is 2.5 and this is 0.5, you may have a good intuition that from A to C, that approximation itself is linear. Okay, so that would have made sense if this was 1.5, which indeed is true. So you can see that F at E was 1.5. Now, the same thing holds if you think about B and D. So B is 1.5, D is 1.5. So they are basically the same value. And you can imagine in this direction, you would get just a constant surface. Does it make sense? So again, you have this surface, which is very difficult to draw, but you can draw it using MATLAB or something because you already have the function. You can draw that. But you may have a good feeling that that surface, let's say from left to right, at the center, or from top to bottom, at the center, it would be linear. Okay, so maybe you can imagine that. Not from corner to corner. From corner to corner, you get these higher order terms. But from left to right, or on the edges, maybe you can have a good feeling it should have a linear shape. Does that make sense? All right, so this is a kind of a crash course on approximation using two-dimensional finite elements, but the element we had now was the simplest element. It had 4 points, or in this example, we talked about 4 points. This would be what we will call a 4-noded element. What we want to do next is to talk about more interesting elements. So the finite elements in 2D, remember we also talked about naming these elements. So the finite elements in 2D are a lot, or there are many different elements. For our purpose, we list only 5 of them. So there is this thing that we just talked about, and we will talk after the break about that in more details, but this is the one. So this is D2QU4N. Then we have D2QU, let's say 8N, sorry, 9N. And then you have D2QU8N. The order is reversed because 9 is easier than 8, or it's more standard. And then you have this D2TR3N and D2TR6N. So the idea or the way we name them is very similar to what we did before. D2 at the beginning, it tells these are two-dimensional elements. The 2 other letters, they tell you what type of element you're talking about. So QU stands for quadrilateral. So these are the elements that they look like this. And then TR, these are triangular elements. Okay. If you look from top, quadrilaterals or quadrilateral elements, they look like square basically. And well, triangles, they look like triangles. In fact, triangles, they look like right, triangles with right corners. Okay, so this is the way they look like. And then 4, 9, 8, 3, and 6, these are the number of nodes on those elements. So if you think about the first element, this is the element which had 4 corners or 4 nodes. If you want to have 9, this is how it is. So those 9s are like this basically. So one of them is like a linear element. It's 2 nodes on each side, so it gives you 4. The other one is like a quadratic element, so 3 nodes on each side. So 3 by 3 is 9. And then this one is a particular type because it is allowing you for having more nodes on the sides, but not at the center. So there is nothing at the center. So this is quadratic on the side, but not at the center. So it's a typical, or it's a particular type of element that we learn as being let's say a non-standard element or a surprising element. We will talk about this after the lecture. But for now, this is the story. We have different types of elements, regardless how you name them or how many nodes they have. The idea is that you can construct shape functions for each of those elements, and you can approximate functions on those elements using those shape functions based on exactly this approximation that we learned here. So this formula itself, it's generic. Regardless what you have, you can always say f of c eta is just ni fi. Okay, this always holds. All right, it's 2:30. Let's have a 10-minute break. We start at 2:40 sharp. All right, so we are back. As promised, we want to go through these elements and we want to write their shape functions together. So we start with the first element. It's basically identical to what we had done just now, but I'm going to write it in a slightly different format because we are going to repeat it again and again for the other ones. And then we go to the next ones together. So the first element is D2 QU 4N. This is also referred to as linear quadrilateral elements. Okay, and then in our Xi eta coordinate system, so if you think of your coordinate system being Xi and eta in its sides or on its sides, let's say this would look like a square, and the square has dimension 2 on each side. So that was my reason to use Xi and eta and the dimension 2 for the other example too. And this would be your origin of the coordinate system, and then you have the directions Xi and eta. Like this. And then these 4 corners or nodes 1, 2, 3, 4 are this. So this is node 1, node 2, node 3, and node 4. And then again, the coordinates of these nodes are -1, -1, 1, -1, then 1, 1, and -1, 1. And according to what we had just together with in the previous example, and we learned together, the first function n1 would be 1/4 1 minus Xi times 1 minus eta, and 2 would be 1/4 1 plus Xi 1 minus eta, and 3 is 1/4 1 plus Xi 1 plus eta, and n4 is 1/4 1 minus Xi 1 plus eta. All right, so this is basically your linear quadrilateral elements. If you think of these 4 elements that we just or the 5 elements that we discussed, you can also see them in this sort of presentation style. And as I mentioned, what we want to do is to go through them. So this is the first element. So basically bilinear quadrilateral element. And after we talk about these 5 elements together, we will also talk about the quadrature rule, the Gauss points for these. So that was basically our element 1, and now I'm going to put it here. So these functions that we had here are basically the same as this. So this is your element. These are how the nodes are arranged and the edges, and then you have the coordinates for each nodes, and you have the shape functions, and you have their derivatives with respect to each coordinate. Okay, so because now there are 2 coordinates, you have derivatives with respect to each coordinate separately. All right, so that was our first element. The second element is it's quadratic quadrilateral element, or biquadratic, because it has it's quadratic on both directions. But let me just write it as quadratic here for simplicity instead of biquadratic. So it's quadratic quadrilateral element, and it has 9 nodes. So it's not 4, it's 9. And those nodes are numbered as follows. So see, we don't want to change the numbering of the corner nodes. So we still call this 1, 2, 3, and 4. And by the way, we always go counterclockwise. Now, node 5 would be your node, your new node here. This is node 5. This is node 6. This is node 7. And all of this is, by the way, in your natural coordinate system. This natural coordinate system is now xi and eta, right? It's not xi alone. This is node 8. And then node 9 is that center node, basically, which coincides with the origin. Okay. So this is your quadratic element. Now, if you want to write the shape functions, you play exactly the same game. N1 is that shape function here. So it should be 1 at this point, and it should be 0 elsewhere. So 0 elsewhere, it means it is 0 along this line, it is 0 along this line, it's 0 along this line, and it's 0 along this line, right? So if you multiply the, let's say, the equations from those lines, you get something which relates to the shape function. So it would be 1 over 4, 1 minus xi times xi times 1 minus eta times eta. So again, you can see if, for instance, if xi is 1 or xi is 0, so xi is 0 means this line. Xi is 1, it means this line, right? So you can clearly see if xi is 0 or xi is 1, it's gonna be 0. So it's 0 on all these nodes. And then you also need to make sure that it's 0 at these 2 nodes. So that would be then where you multiply it by 1 minus eta and eta. All right. So that's how you construct, for instance, N1. And then if you think of N, I don't know, let's think of N2, N3, and N4 are similar to that. And let's jump to N5. Now, N5 would be something that is 1 here and is 0 elsewhere. So now you would multiply, or you would make sure that it is 0 on these lines. Okay, so it's gonna be 0 elsewhere, and then we need to have it as being 1 on node 5. So if you do that, your N5 would look like minus 1 over 2, 1 minus xi, 1 plus xi, 1 minus eta times eta. Okay. So again, you clearly see that if you have this, if xi is 1 or if xi is minus 1, or if eta is 1, or if eta is 0, it's going to be 0. So it makes sure that it is 0 on all the other nodes. It's only non-zero at 5, and then by multiplying it by minus 1 over 2, you make sure that it's actually 1 at node 5. And then eventually, let me write N9. N9 would be 1 minus xi, 1 plus xi, 1 minus eta, and 1 plus eta. Okay, so that would be your quadratic quadrilateral element. And by the way, it is also usually called Lagrange quadratic element. Okay, so just, it's a Lagrange quadratic element. And if I want to just show you the slide associated with that, it looks like this. Okay, so again, you have this element. That's exactly how we have it. These are the nodes. So 1, 2, 3, 4, and then 5, 6, 7, 8, and 9 is at the center. These are the shape functions, and these are their derivatives with respect to each coordinates. Okay. All right, so that's that. Now the next one would be 8-noded quadratic quadrilateral, and that one, because it's 8-noded, it's it's called serendipity quadratic quadrilateral element. The property of this one is that node 9 basically doesn't exist, if you want. Okay, so it's 8-noded. Those 8 nodes are exactly similar to what we had for the 9-noded element, except that now you have no node at the center. All right. Now, for this element, if you want to construct the shape functions, you would do like this. You would assume that it is, for instance, 0 here. It is 0 here. I'm talking about N1. And it's 0 along this line. Okay. Then this would be the way you get N1. But it makes sense to you, right? I mean, if it is 0 here, then that means it is 0 on all the other nodes. But because we don't have that node at the center, we don't want it to be 0 at the center. So we construct those lines like this. Okay? So if you do that, your N1 would look like, I don't know, -1/4, 1 minus C, 1 minus eta times 1 plus C plus eta. Does that make sense? So if you look at this now, if C is 1, or if eta is 1, you are talking about these two lines respectively. So this is C equals 1, and this is eta equals 1. So you want to make sure it is 0 on those two lines. Perfect. Those first two terms, they do that for you. The second one is basically the equation of this line. Okay. So you want to make sure that on this line it's 0. For instance, think of 0.5. For 0.5, C is 0, eta is -1. So if you add that here, you get 0. Okay, so it's 0 on node 5, it's 0 on node 8, it's basically 0 on that line. And that, as I mentioned, this is essentially the equation of the line. The equation of this line is something like C plus eta equals -1. Right? So that means if you just bring this to the left-hand side, you always get 0. All right, so that would be your N1. And you may ask yourself, why are we doing this? If you compare this is N1 for a serendipity quadratic element, to your N1 of a Lagrange quadratic element, you see the order changes. So this is, I mean, you would have a quadratic term in C and quadratic term in eta. So if you want, you can think of it as a fourth order term, because you have quadratic term in both. But now this gives you a third order term. Okay, you don't get a quadratic term in both. Okay, so the highest order you see is one order lower. So maybe that has advantages for you. It has certain properties, and we will talk about that when we do examples, and also in your homework and in your project. You will implement these different elements, and you have the chance to change between the elements and, let's say, analyze their influences. Okay, so that's something we will learn later. But for instance, in this case also, if I want to write N5, that would be N5. So you can see it's kind of one term lower compared to its Lagrange counterpart. Okay, so that would be, again, this element. So basically, this is the serendipity by quadratic element. And you have the shape functions listed as well as their derivatives. Okay, so we want to do two more things, and they are the triangular elements. So we talked about these ones, okay, or let's say in this case, we have done the first three. We just want to learn what happens if you have triangular elements. So if you have triangular elements, you can imagine a few things will change. Yeah, let's just draw everything. So the first thing would be linear triangular elements. Linear triangular element. This element is very famous. This is also referred to as CST, or constant strain triangle. And this is kind of the oldest element, if you want. So constant strain triangle. Or constant stress triangle. It doesn't matter because strain and stress are the same order, let's say. If you think about this one, we call this linear quadrilateral. But if you look at the shape functions, I mean, they are linear in each term. So they are linear in C and linear in eta. But the shape functions themselves, they are not linear. They are of order 2, right? So that is the difference between a triangular element and those functions. Here, when you say linear triangle, the shape functions are really linear. Okay, so we draw our element again in our natural coordinate system. So let's say this is your natural coordinate system, or this is the triangle in that natural coordinate system. Now, the nodes are here, so that's node 1, node 2, node 3. And your coordinates are exactly the same way that you would imagine they would be. So they are C and eta like this. And node 3, in this case, it would be at 0, 0. So node 1 would be at, let's say, 1, 0. And node 2 would be at 0, 1. So again, we want to construct these shape functions for this element. And let's look at that. N1, N2, and N3. So N1 is a function that must be 1 at node 1, and it must be 0 at 2 other nodes, which are node 2 and 3. So it's simply Xi. So if you just say N1 is Xi, here at node 1 you get 1, at node 3 and at node 2 you get 0. So that's N1. N2 is simply eta, and N3 is 1 minus Xi minus eta. Okay, so again, this is the line here is Xi plus eta equals 1 now, right? So if you write that as N3, you make sure that it is 0 on this 2, and then it's 1 here. So these are the the shape functions for a triangular element, for a linear triangular element. And as I mentioned, the nice property with these is that when you say they are linear, they are really linear. And now if you calculate their derivatives, for instance, n1 xi, that gives you a constant, and then n1 eta, that gives you a 0. You don't have this property for other elements. Okay, and then maybe you can imagine that your strain is related to the derivatives of shape functions. So if you have constant derivatives for the shape functions, maybe you can imagine why your strain should be also constant. Okay, so this is your first triangular element. And as I mentioned, this is possibly the most famous element. It has some nice properties and some issues also, but again, because of its let's say historical significance, you should not dismiss it just because it has some issues. Okay, so that is your linear triangle, and then the next element we want to talk about is the quadratic version of this. So that would be 6-noded, and that would not be linear, so it's quadratic triangular element. So if you have a quadratic triangular element, you would have additional nodes in between. So these are your extra nodes at the center of each of those edges. So this would be node 4. Again, we go counterclockwise and we keep the corner nodes as they were before. So 1, 2, 3 remain the way they are. Now between 1 and 2, you would have 4, then 5, and then 6 here. So you play the same game when you want to write the shape functions. Again, for instance, here, when you want to write n3, you make sure that it is 0 on these 2 lines. Okay. So you write these functions like that. And again, if you want n1, you make sure that it is 0 on these 2 lines. And if you want n2, you make sure that it is 0 on these 2 lines. Okay. So you play our famous game, and n1 would be xi times 2 xi minus 1, for instance. And you can similarly write n2 and n3. And I don't know, n4, for instance, would be 4 times xi times eta. And you can similarly write n5 and n6. And then again, I have prepared this slide for you. So you have them here, basically. So this is n1, n2, n3, n4, n5, and n6. As you can see, again, here, when you talk about triangular elements, when you say they are quadratic, they are really quadratic. Okay, they don't have that higher order. So a quadratic quadrilateral element, it gives you something of order 4. Here, actually, a quadratic triangular element, it gives you something that is quadratic, is of order 2. All right, so these are the elements themselves. Now, in order to make sure that you remember these, and you kind of have a geometrical feeling about them instead of just writing formula, I want to also show them to you, or I want to show their plots to you. But do not remember, we are not done yet. We talked about these 5 types of elements, but this quadrature rule, the Gauss points or the integration points, we have not talked about. Okay, so we will shortly come back to that too. But before that, let me just jump to these shape functions. Now, if you have, for instance, a 4-noded element, so this is your D2QU for N. Okay, so this is D2QU for N. And this would be node 1 of that. Sorry. So if you look at that, again, maybe you should think of it like this. Let me just look from top. If you look from top, I don't know if you think it's top. If you look from top, this would be, or the node here would be node 1, node 2, node 3, node 4. All right. So it was like that, and basically we expected at node 1 to be 1. So you see that, right? But at the other 3 nodes, it's 0. I don't know if you can appreciate it, but you see how it is, right? So at the other corner nodes, it is 0. And at that node, at node 1, it's basically 1. You will see more of them, and they make sense. So for this function, it's 1, 2, 3, 4. They are similar in that sense. If you think of that, let's say the quadratic quadrilateral one, so the 9-noded one, maybe that's a better example to show to you how they look. It's like this basically. Again, if you look at this guy, the node that comes up, that would be your node 1, right? So maybe you should think of it this way. So this node is node 1, and then maybe let's say the horizon is like that. So if you look from this side, it's quadratic. So if you look from left, you see this quadratic line. If you look from this angle, you also see that quadratic line, but I hope you can appreciate that it is now 0 at every other point. So yeah. Let's see. So the points are, let's say here, or the nodes, they are these points, and they are all 0, okay, the way they are. But then it's exactly 1 at that corner node. So this was N1, and you can imagine N2, N3, N4 for a 9-noded element. They all look similar to this. It's just a different edge is coming up. Okay. Now, if you want to think of N5, remember 5, 6, 7, and 8. They were at the center of each edge. So they are going to look like this now. These are like basically these curves that now they are 1 at that center. So that would be your node 5. Again, if you think of the element, and let's say this would be that edge, and this would be node 5. Okay. Maybe this was node 1, this was node 2. So you can see that again at all the other nodes. So that would have been 3. Sorry, 1, 2, 3, 4. Yeah. 5, 6, 7, 8. This would be the way that we had the nodes. So it's 0 everywhere else. It's only at 5, it's 1. Okay. So again, 5, 6, 7, and 8, they have these nice shapes. And then 9 itself, it's just at the center, right? Remember, node 9 is exactly at the center. So this is how the shape functions for node 9 would look like. You see, it's just basically a bubble that is just one exactly at the center, and it's zero everywhere else on all the edges, because the other nodes 1, 2, 3, 4, 5, 6, and 7, and 8, they are all on the edges. Okay, now these are let's say linear and quadratic elements. For the linear elements, I wanted to also emphasize on one thing. So remember that I told you, although we call this a linear element, so if you have a quadrilateral, you call this a linear element. It's only a line on the edges. So if you look at this edge, it is a line, right? And if you look at the other edge here at the back, it's also a line. But you can see it is actually also, it is a curve in the center. I don't know if I can, let me see if I can make that more obvious. Yeah, maybe that's not too bad. So do you see what I'm trying to say? That from this corner node to this corner node, it is not a line. It's actually a quadratic function, but these are straight lines. So on the edges, you get straight lines for that element, but at the center, you get that shape, which makes sense. I mean, if you just take a piece of paper and let's say you glue the three corners to the table, and you want to pull one corner up, you see you need to make a curve on that surface. So these are, let's say, four node or quadrilateral elements. If you had quadratic elements, it would be the same game. So for instance, if you had a linear triangle, you would have, again, one corner that is 1 and the other two are 0. So this is pretty straightforward. This is kind of boring. But then if you look at the same shape function, so n3 for a quadratic triangle, now it looks slightly more interesting because it does this nice thing. And then you can clearly, I don't know if clearly, but you can see that let's say on this edge, so if you come here, there are also these 2 points that are also 0. So you would have 3 points here, and you have 2 points here that are 0, and then only that corner that you have there, it's 1. And again, if you think of that intermediate nodes of that quadrilateral, of that quadratic triangular element, you can also see something like this. Okay, so again, this is a triangle. So if you can, I don't know if you can see that. So it's basically a triangle, but it looks like this because that one shape function is coming up. All right, so these are, let's say, individual shape functions, but then I also nicely have these combinations of them. So hopefully they will help you better see what's happening here. So if you think about these, so these are these shape functions, and they have the same order that we had used for our element. So remember, if it was a D2QU4N, so 4-noded quadrilateral element, if you remember, we said that it has 4 nodes, and the nodes are 1, 2, 3, 4. Okay. Now on this plate, I am showing exactly those shape functions in the same order that we numbered them in our notes earlier, and you can kind of see what they do. So N1, I mean, first of all, they are sort of geometrically similar, but then you can see that N1 is coming up, or is 1 at node 1, is 0 elsewhere, and 2 is 1 at node 2, 0 elsewhere, and so on. So these are the 4 shape functions for linear quadrilateral element. If you have that 8-noded element, again, we play the same game here. Okay, so now you have these shape functions, again, the order of the nodes, they are the same way that we numbered them. So n1 is lower left corner, n2 is lower right corner, and so on. And these would be the way that those 9 shape functions look like. And then you can imagine exactly how they make the edges of your elements or the shape functions. And then we play this game also for this 9-noded one. So this is, let's say, the Lagrange 2D element. And you can clearly, again, see the same story that if now you look from top, by the way, this is, again, node 1 would have been here, node 2 here, node 3 here, 4 here, 5 here, 6 here, 7 here, 8 here, 9 here, right? So if you just think about this, it's exactly the same order that we drew previously, and now you can kind of appreciate, I hope you can appreciate, let's say, the way they look. Okay, so these are that, and then as I mentioned, we have also these triangular elements. So this is your constant strength triangle. That is the, let's say, the most simplistic one. So that is your n1, n2, n3. So they are like flat triangles for each of those. And then you have this so-called quadratic triangular element. Okay, so you have now this one. Again, the same sort of order. So if you look from top, you see that ordering, the numbering that we just had together. So for a triangular element, remember 1 was here, 2 here, 3 here, and this was 6, 4, and 5. Okay, so the numbering is exactly as we showed together in our notes. All right, so I hope these shapes, they help you understand how to draw these sort of shape functions. It's very similar to what we have done in 1D, but in 1D, because they were curves, it was so simple to do that. There is one last thing that I need to just quickly tell you, and that would be the Gauss Quadrature. Now, Gauss Quadrature is pretty simple for this. It's very straightforward, and it's exactly similar to what we did before in 1D. If you have a triangular element, this is the way that you would do that. So you usually have a double integral over that triangular surface. Now, instead of that double integral over the triangular surface, you would have a summation over Gauss points times some weights and some evaluations at those specific Gauss points. And if you have 1 Gauss point, the weight would be 1. The coordinates are here. If you have 3 Gauss points, the weights are 1/3, and the coordinates are here. Now, if you see, the weight here is 1, and then the sum of these weights is also 1. Okay. Now, if you think of it, the sum here is 1, and then this is again 1. Now, that 1/2, if you multiply it by that 1, that is exactly the area of the triangle that we had. So remember, the triangle in a natural coordinate, it has these corners 1, 0, 0, 1, and 0, 0. So the area was 1/2. Okay, that 1/2 is exactly the 1/2 that you have here times the sum of the weight factors. So why am I saying that? Because if you think of the same integral, but now not for triangular elements, but for quadrilateral elements, if you see now the weight factors is 4. Okay, so there is a 1 here instead of 1/2, and the weight factors are either, if it is 1, it's 4. If it is 4, it's 4 times 1. And if you have even more Gauss points like this, if you add them up, it's 4. Okay? Again, this 4 is the area of that element. Remember, the coordinates were from -1 to 1 on each side. Okay, so the area is 4, that's why your weight factor, if again, if you have 1 point, it's 4. If you have multiple points, the sum is 4. Okay, it was very similar in 1D. So in 1D also, you remember your natural coordinates, for instance, if you had your natural coordinates c from -1 to 1, the sum of your weight factors there was 2 to, for instance, to recover that. All right. So anyway, this is also the, let's say, quadrature rule for two-dimensional elements. The only important thing for you is that if you have a triangular element, or if you have triangular elements, do not forget the factor 1/2 here. Okay. If you have quadrilateral elements, you do not have a factor. It's just basically a 1. All right. That's all for today. So we learned everything that we wanted to learn regarding approximations using, let's say, two-dimensional finite elements. So we learned 5 types of elements, and we saw how they look like, or the shape functions look like, and we also talked about two-dimensional quadrature rule. With this, we can jump to actually the methodology of the finite element method in 2D in the next lecture. Thank you very much for your attention.